David, we're familiar with the strange concept of quantum mechanics that tells us that two contradictory things can both be happening at the same time. How do we deal with that?
Quantum mechanics is often said to inform us that two contradictory things can be happening at the same time. I'm not sure I think that's the most accurate way to describe it. Rather, at least on the standard view of quantum mechanics, it's something like there is a pair of things, one or the other of which we think must be happening, whereas quantum mechanics tells us that there just fails to be a fact about which one of them is happening. So that, for example, quantum mechanics tells us that there are certain circumstances in which we know an electron is either here or here, but if we ask which location it's actually in, it's like asking, say, for the weight in grams of Catholicism. Or for the marital status of the number 5, or for the political affiliations of a tuna sandwich, or something like that. It's a question that fundamentally doesn't make sense, and this is very, very strange to us, because we think questions, say, about the locations in space of material objects must always make sense. Good. Moreover, it's not just a matter of what we think, it's not just a matter of what our prejudices are. We always see material objects in perfectly determinate spatial locations.
When quantum mechanics tells us that that's not the case.
Exactly. When quantum mechanics tells us that at least there can very often be circumstances which we have encountered often, in which that shouldn't be the case. The fact that quantum mechanics in certain instances seems to deny that there are determinate outcomes of these measurements is what's referred to as the measurement problem in the literature. And there have been a variety of approaches to trying to solve this problem. Most of the conventional such approaches have to do with modifying the fundamental quantum mechanical laws so that those laws do yield one or another determinate outcome of such an experiment. There's another more radical attempt at approaching this problem called the many worlds interpretation of quantum mechanics, which simply denies that the measurement has any particular determinate outcome, and which rather speaks of a pair of worlds being created in the course of such a measurement, in one of which the measurement has one outcome, and in the other of which the measurement has another outcome.
And in that branching system, as you have those decisions being made, it becomes enormously complicated, and the number of worlds that are in that concatenation exponentially are beyond number.
That's correct. That's correct.
And that seems to be wildly against our intuitions, but many physicists are now moving more towards that.
That's true. It's becoming more and more popular.
Do you find that astonishing?
Well, I think there are deep problems with the many worlds interpretation. I don't think the problem is that it's counterintuitive. We've had plenty of that in physics before, and we've had to get ourselves used to that any number of times. I think the problem is that at the end of the day, it may not give us an account of our empirical experience of the world in the way it's designed to. Here's the specific locus of what I see as the problem. There are two things that the world tells us about how measurements come out. One, that there is a determinate fact about how they come out, that they come out one way or another. The many worlds interpretation explains this as an illusion and does a good job of explaining it as an illusion. But there's another fact, which is that they come out this way or that way with certain particular probabilities. That if we do the experiment many times, it'll come out this way or that way with certain particular frequencies. This is something that, on my view, the many worlds interpretation is going to have much, much more difficulty explaining. Because on this interpretation, both of the possible outcomes occur with certainty every time. This is, in a certain sense, a completely deterministic theory. You know which experiments you're going to do. You know exactly what's going to happen. You're going to get this result and that result of the first experiment. You're going to get this result and that result of the second experiment every single time, for sure. It's very hard to see, or hard for me to see. Now, this is a story, this is a question that's been intensively discussed over the past 20 years or so. There have been lots of twists and turns in this discussion, but very, very crudely, to sum it up in one sentence, there is a deep problem, on my view, associated with the question of how the many worlds interpretation can possibly account for the probabilities of this or that outcome that emerge in our experimental experience of the world.
So what do you have that's better?
Oh, well, there are these other approaches to the measurement problem that I was mentioning before that involve actually modifying the equations of motion, that involve adding additional variables, so on and so forth.
So you're fiddling with the equations of quantum mechanics,
yes.
which the many world people will say you're distorting.
Exactly that. That's exactly right. And what is most potently alluring and attractive about the many worlds interpretation is that it doesn't fiddle with the basic equations at all. This is great, okay? But if at the end of the day it doesn't account for our experience, doesn't matter how pretty it was, it doesn't account for our experience. So I'm very sympathetic to the motivations of the many worlds interpretation. I understand it very well, but we need to ask very resolutely whether it's actually accounting for our experience or not. If it doesn't, then nature is telling us that we have to fiddle with these equations.